ignition and liftoff of Columbia on an ambitious 10-day international research flight.
The critical fluid light scattering experiment is an exciting part of the second United States microgravity payload that will fly aboard the Space Shuttle Columbia. This precise experiment will challenge the universal understanding of some physical phenomena. The experiment is named ZENO, in honor of an ancient Greek philosopher, Zeno of Elea, who first pondered the concept of infinity. Zeno's most famous paradox of infinity demonstrates that an infinite number of successively smaller steps can be squeezed into the distance between 2 points. Zeno's paradox is analogous to the modern-day ZENO experiment, where a series of minute steps are made toward the critical temperature of a fluid. The critical temperature of a fluid is the highest temperature at which its liquid and vapor phases can coexist. At low temperatures, both the liquid and its vapor can be observed and exhibit on Earth a visible meniscus or boundary. At temperatures above the critical temperature, only a single phase exists. The ZENO experiment will begin in this supercritical single phase region and will progress toward the critical point to study fluid properties as the fluid prepares to separate into 2 phases. This is an example of a second-order phase transition. Other examples of second-order phase transitions include normal conductor-superconductor transitions and magnetic transitions at the Curie point. At the critical temperatures of these second-order phase transitions, the materials fluctuate between different states. It's these fluctuations that scientists want to study. Much progress has been made in theory and measurement of these phase transitions, but the Earth's gravity makes it impossible to do a careful study of the secondary liquid-vapor phase change at the critical temperature. Fortunately, the space environment now permits a new generation of experiments to test the best theories currently available. ZENO principal investigator Robert Gammon explains why the gaseous element xenon was chosen for this experiment.
We believe that xenon is an ideal fluid for studying the liquid vapor critical point. It's available in very high purity, it's a simple, monatomic, spherical atomic fluid, and it has a convenient critical temperature. It's better than all the other systems we could think of for very precise studies close to the critical point because it's not limited by purity and not limited by crystal perfection.
The ZENO experiment is being done in the microgravity environment of space because on Earth, as you near the critical temperature, the Earth's gravity causes the fluid to stratify or form layers. This distorts the sample. But the microgravity environment of space permits a very close approach to the critical temperature before the stratification begins. During this experiment, careful control of the sample density and thermal environment enables precise measurement to be made within a few millionths of a degree of the critical temperature, 100 to 1,000 times closer than is possible on Earth. We might compare the experiment to climbing a mountain. The goal is to analyze the area closest to the peak, the critical point. To do that, the climber makes minute moves toward that point. As the climber gets closer, some unusual things happen.
It's fascinating. Xenon, near the critical point, is 1 billion times softer than water. The system doesn't know whether it wants to be a liquid or a vapor, and it readily goes back and forth between the two and has nearly an infinite heat capacity. In the process of this sloshing back and forth, it turns milky white.
It's in this state that important measurements will be made. As the temperature of the fluid sample in the ZENO experiment approaches the critical temperature, density fluctuations increase dramatically. A laser serves as a gentle probe that is sent into the sample to measure those fluctuations. The sample becomes turbid or cloudy and scatters light strongly. This experiment can be compared to the familiar twinkling of stars we see in a clear night sky. The twinkle we see on Earth is due to fluctuations in the density of the atmosphere. During the experiment, laser light that is being scattered by the sample actually twinkles. Here, the twinkling is due to density changes in the fluid as it nears the critical temperature. The ZENO instrument will measure and analyze the brightness and frequency of the twinkle as the fluid nears the critical temperature. Under the direction of Professor Gammon, a team from the University of Maryland defined the science requirements for the experiment and developed the flight instrument. The instrument was fabricated and tested by Ball Aerospace.
The heart of the experiment is a high-pressure sample cell located in the thermostat. This sample is illuminated by a laser, which is brought around through the apparatus with mirrors and a beam splitter, and in along the axis from either end. The sample is located close to the center of this thermostat and scatters light to this photomultiplier at a small angle, or through a bending mirror to a second photomultiplier, so that we can see two angles at once. The other principal detectors in the experiment are photodiodes, which sample the light behind this partially transmitting mirror, and there's one at the other end as well.
The ZENO instrument will fly aboard the Space Shuttle Columbia as part of the second United States microgravity payload. This series of payloads has been sponsored by the NASA Office of Life and Microgravity Sciences and Applications. These payloads include some of the most challenging experiments to be conducted in space during this decade. ZENO will provide data that is not observable on Earth. Theories will be challenged, and experience will be expanded. Improved understanding of second-order transitions will help enhance theories that may have an impact on many scientific fields.